Hi, my name is Aggie Branczyk, and I'm a manager for quantum applications research and software at IBM Quantum. And today I want to tell you about a new software prototype that we're developing based on a paper that came out of IBM Quantum entitled Doubling the Size of Quantum Simulators by Entanglement Forging. This paper was recently published in PRX Quantum. Now, with this software prototype, you'll be able to get your hands on entanglement forging, reproduce some of the key results from the paper, and see whether you can apply entanglement forging to some of the problems that you're interested in solving. In this series of videos, we're going to give you everything that you need to get started. In this first video, we're going to look at some of the background concepts and theory that you need to understand entanglement forging. And in subsequent videos, we're going to look at the software package itself. We'll give you a tour of the GitHub repo, show you how to install the package, and even go through some of the tutorials. So what makes entanglement forging so useful? Imagine you wanted to simulate the ground state of a water molecule, and for your particular simulation, you are going to use 5 molecular orbitals. So each of those orbitals can contain 2 electrons, a spin-up electron and a spin-down electron. So that gives us 5 spin-up electrons and 5 spin-down electrons. Now, if you were going to use a regular VQE, you would map each electron to a qubit, and you would need a 10-qubit circuit to do the simulation. But what entanglement forging does is that it recognizes that the spin-up subsystem is only weakly entangled to the spin-down subsystem. So we can use a quantum computer to simulate the spin-up subsystem using only 5 qubits, and use a quantum computer to simulate only the spin-down subsystem using only 5 qubits, and then use a classical computer to forge the entanglement between the 2 subsystems. And in doing so, we can double the size of a simulation that we can do on a quantum computer using the same number of qubits. So now I want to hand over to Tanvi Gujarati, who is one of the co-authors of the paper, and she's going to dive a little bit deeper into the theory behind entanglement forging.
So just a quick review of what entanglement forging is. So let's assume that we have a system given to us, which is described by this Hamiltonian H, described over 2n qubits, and a wave function that's psi, also over 2n qubits. And we wish to measure an observable or the expectation value of H, and is described by M, which is just the quantity shown here. So one can perform a Schmidt decomposition of the wave function in such a way that your system is divided in parts. So in this particular situation, just let's consider that it's an equal division between the 2n qubits into 2 subsystems of n qubits each. And the lambdas here would be what you call the Schmidt coefficients for such a decomposition. In general, you would have exponentially many Schmidt coefficients, exponential in the size of the subsystem. So 2 to the power n would be the maximum number of Schmidt coefficients. But if there's weak entanglement between the 2 systems, then the significant values of lambdas will be few. And if the 2 systems are maximally entangled, then you would have all of them have non-zero Schmidt. Basically, the Schmidt rank will be full. So now we can also partition our Hamiltonian, which essentially for these molecular systems is just a sum over many Pauli strings into the 2 halves as well. So each Pauli string here is basically describing just half of the system, and it's summed over with certain weights. So when we combine these 2 equations into the expectation value again, what you obtain is that it's a superposition of many small expectation values. Here, note that the terms that within this particular inner product are different. The bit strings x and y are different, but there are ways in which you can simplify this to just a simple expectation value calculation. So again, that's just a side detail. We don't have to bother about that right now. But essentially what this summation is telling you is that the expectation value for the full system, which could have been described by a circuit with 2n qubits, can be obtained if we were to calculate these independent terms on the quantum computer with n number of qubits instead of 2n, and then sum them over with appropriate weights. Okay, so that's the philosophy that will be used, and a large experiment like the experiment over 2n qubits is now replaced with a weighted sum over many small or n qubit experiments. Okay, and how does one use this for the case of simulation of molecular systems? So in this particular case, if we consider just the molecular system, then the wave function that we obtain, let's assume the ground state wave function, can be split based on the spin up and the spin down part of the electrons. And in general, it's observed, or I mean, at least for many molecular systems, you can calculate the singular value decomposition and find that the singular values decrease quite rapidly. That means only a few singular values are important if we divide the system along the spin up and the spin down sectors. And that's essentially the division that was used in the entanglement forging paper. And actually, they are saying that the Hamiltonians for the molecular systems fit the bill for entanglement forging calculations. Just one point I want to highlight is that in certain cases, when there is symmetry between the spin up and the spin down sectors, you can use the same unitary for representation of this singular value. So you don't need U and V to be separate. They could just be the same unitary. Okay. And so how do we actually find or use this decomposition to get some ground states? Because a priori, the whole purpose is to find the ground state. We don't know what it is to begin with. So the way we do that is we create an ansatz of sorts. So we assume that our Schmidt decomposition has X number of terms, or not X, let's say has some terms in it, because X already is a variable used here. So let's say that it has some number of terms which are important. Those would be some free parameters that we have. What are the exact values of the Schmidt terms that we consider? That is free to decide, or a variable. And then also the unitaries that we use in the Schmidt decomposition, which would be U or V, depending on whether you have to choose it similar to each other or not. So the angles in these unitaries as well as the Schmidt coefficients are parameters that one can start with and then optimize just as you do in VQE. So the content here in this dashed blue box is essentially the Schmidt decomposition step, and then that would give you ansatz for wave function, and then by using classical optimizer, you can update the parameters in this ansatz repeatedly till you converge.
Thank you, Tanvi, for that great overview of entanglement forging. In the next videos, we're going to look at the software prototype itself. We'll give you a tour of the GitHub repo, we'll show you how to install the prototype, and then we'll look at a particular tutorial. And at that point, we'll be able to make connections between what's happening in the software and the theory that Tanvi just described. So I look forward to seeing you in the next video. Bye.